When I was growing up, I remember having telephones at home. Generally, they hung on the wall and they had a long telephone cord. And a typical thing, if you were talking for quite a while, would be to swing the cord up and down, resulting in what is known as standing wave motion. In this experiment, you'll have an opportunity to see standing wave motion for yourself. Also, within the physics, there are some very particular and relatively simple mathematical relationships between frequency, wavelength, and velocity. With this experiment, you need a small metal slinky, and by shaking it back and forth and determining the frequency and measuring the wavelength, you'll be able to calculate the speed of the wave in the slinky. But then, by knowing the tension and the mass of the spring, you can get the same speed by a second method. The goal of this activity is to get both speeds and compare them to see how close they are to each other. The materials for this experiment are a standard slinky, a meter stick or equivalent, a spring scale, and a timer. Here is an example of the motion of the spring when you have created standing waves. Here is the example of the motion for the first harmonic. Notice that the distance from node to node is half a wavelength. The second harmonic will look like this. Now the distance from node to node is a single wavelength. The third harmonic will have 3 half waves, so the wavelength is 2/3 of the distance from one end to the other. In order to calculate the speed, we do it by 2 different methods. In the first method, take the frequency and multiply by the wavelength. Find the average for the 3 harmonics. We can also determine the speed from the spring properties. The speed is the square root of the tension divided by the mass per unit length. The tension is measured with a spring scale. The mass of a slinky is around 210 grams, and the length will be the distance from end to end.